let's consider the problem in your assignment or problem set, which was to calculate the surface area of a cone using some coordinate system. So let's first look at how we can use spherical coordinate system to calculate the surface area. Now again, remember, spherical coordinate system depends, in spherical coordinate system you have three vectors. R hat vector, which is a radial vector, which is pointing radially out of your origin. A theta hat vector, which takes that line and turns that line around z-axis, turns the R line around z-axis. And a phi hat vector, which takes this line and rotates it in xy plane to make something like a cone. So it looks like we should be able to use, we're naturally making a cone here, so it looks like we should be able to use spherical coordinate system to be able to calculate the surface area of a cone. So first thing we have to think of is, where should I put the origin of my axis? And obviously the origin, we are trying to make a cone, and you see that theta hat, a phi hat tries to make a cone around the origin, around the point of the origin. That's what phi hat vector is doing. So it's pretty obvious that we should be putting our origin right at the top point, and thus we can make our axis go downwards. Let's call that the z-axis. Remember again, in spherical coordinate system, though the system is defined by r hat, theta hat and phi hat, z hat actually plays an important role because everything is being built symmetrically around z hat axis. So we're going to build this cone symmetrically around the z hat axis. What is remaining constant here? What is remaining constant is this angle, and let's call this angle theta naught. So theta in this problem always remains constant, theta naught. I don't change theta. I don't go to any, to calculate the surface, I don't change theta. What I'm doing is I'm taking this line, this is the line here, I'm taking that line and I'm rotating it around in a circle in xy plane, and in rotating it around xy plane I create that cone. So that's what I'm trying to use. So theta remains constant at theta naught, and with respect to the origin, what do we have? We'll have this line would be my r hat line, and related to that would be, and what is turning around in that direction would be my phi hat term. So my r vector would change. R will change from this point to that point so that I can make this line, and then my phi hat vector would change so that I can make my full circle. So the next step we have to do is go to an arbitrary point on the surface. So what I do, from my origin, I'm going to some arbitrary point A, and at that arbitrary point, I need to think of the surface element ds. What is this arbitrary point going to be defined by? It's going to be defined by this length. How far am I away from the origin? So that would be r. And it's also going to be defined by phi hat. What is phi hat vector doing? It's taking this and it is going to rotate it so that I make the circle. So effectively by vector r, I go to this point by vector phi hat, I make that base of that small cone which I have created there. What would my differential element be? I take a small length this way, that would be dr, and then I take a small element in that direction. With that small element in this direction, what I'm trying to do is create this slice of the cone. So by moving this small element along this direction, I take my cone and I create a thin slice of that cone. This becomes my ds element. What would my ds element be? So this is A, let's call this point A1. And if I see, I get a right angle triangle, which is OA A1 with angle theta naught, this being R. So this length is R sine theta. My phi vector is taking this length and creating an arc length of this time. This angle which I have created is going to be d phi. So the length which I have here is going to be the radius with which I am rotating that element, which is r sine theta, by the small angle I'm rotating it by, d phi. So that becomes the arc length in the bottom place. And thus, my ds element simply becomes dr multiplied by r sine theta d phi, or r dr sine theta, and theta is constant, so I can call it as theta naught, sine theta naught d phi. That becomes this shaded red differential surface element. To calculate the total surface, all I have to do is move this point A everywhere in the cone and keep on adding these surface elements, which is what we do by an integral. So I have to take this ds element and I have to integrate it. What do I have to integrate it on? I have to integrate it from origin, r is equal to 0, which creates this point, till element here, and phi, which makes a full circle, a horizontal xy plane circle, which is 0 to 2 pi. So set up this integral, use this element, set up this integral, and see whether you can get the surface area of a cone. We can also do the surface area of a cone using cylindrical coordinate system. So we'll have to be a little bit careful there. Let's see how we can do that. So if I have to do cylindrical coordinate system, again, let's remember what cylindrical coordinate systems are. In cylindrical coordinate system, you take your axis, and with respect to the axis, you define your r vector. So this vector, this finger here is r, this finger here is r2, and basically the radial distance from this axis is what we call r vector. It's pointing outwards. And phi vector takes this and rotates it around to make a circle or a disk. And then you move this along the z-axis. So you make a differential, you make a cylinder. How would you make a cone as a cylindrical axis? Well, think about it. As you are taking this circle, which you have created with r and phi. So let's say I have created this circle with r and phi. As I move this circle up, I don't keep the radius constant. The radius keeps on decreasing as this moves up. And if I let the radius decrease, I would end up getting a cone. So again, we have to define the coordinate system. So obviously the z-axis should be going through the center. But the question comes is, where should I put the origin? You have two obvious choices here. One choice is you put the origin at this place, let's call it O1. And the other choice is you put the origin at the top. I'm calling it O2. Pause the video and think which one of these would make your life easier compared to the other. Remember, whenever you are trying to do vector calculus, you are trying to look for right angle triangles. If you chose this as the origin, What you would have to do, you have to define some arbitrary place, similar to what we had done before. We have to define this arbitrary differential element. What you would get is this trapezoid for a parallelogram. You'll have to deal with this trapezoid if you chose the origin in this case. Whereas on the top, what you get is a right angle triangle when I have defined my differential element. Right angle triangles would always make your life much easier compared to trapezoids. So it is very clear that instead of calling the origin here, we should be calling the top to be the origin. And if we are calling the top to the origin and we are defining the cone, we can easily call something going down as your z-axis. This is the arbitrary point where we have defined our differential element. And I want to be able to calculate ds in terms of my coordinate system. And what do we define? We define how is cylindrical coordinate system defined. Cylindrical coordinate system is going to be defined by distance. So that distance, one thing would be the distance z from the origin, how high you are on the axis with respect to what you're calling the origin. The other is going to be defined upon how far you are from this axis to this point. So that is what is called r in cylindrical coordinate system. In spherical coordinate system, r is from the origin to a point. In cylindrical coordinate system, r is from the axis going through the origin to the point. So this length of the blue marker would be r. This would be r for spherical coordinate system. So we call this r, and again what we have here is we are trying to create, just like spherical system we've done before, we are trying to create a differential ring like this first, and then go to different z's and add the different rings. So again we have, let's make a right angle triangle once we have identified it. We have O, A, A1. This is R, this is Z. This angle we had previously said was theta naught. Let's keep it theta naught. We see that R by Z is tan theta naught. So R is a function of Z. We have to find ds. The ds element at that point A depends upon this length, and it depends upon the length here. This length is pretty straightforward. That is basically, I have, with respect to this origin, we are at R, and I am trying to create a disk of this element here. So that length is just this arc length where I change the angle by a small amount. So that length is simply r d phi, defined in terms of spherical coordinate systems directly, cylindrical coordinate systems directly. So that length is r d phi. However, the length which we have on the side is not dz. This length, so we have a cone. This is the surface of the cone. Z is going downwards. We have taken a small subsection of this length, which is going to be slightly larger than the small subsection in Z. So let's call this dl for the time being. What do we have? We would have a step which we have taken. So I'm taking this element and I'm blowing it up. This is dl. dz is the vertical step we take as defined by the system, and this angle is theta naught. So when I put my element here dl and dz, this angle would remain same as that angle, so that would still be theta naught. Then you have a right angle triangle. So what it tells you is you have this dl, your surface element is the length here multiplied by this length, which is equal to that, and that becomes r d phi dl. But remember, when we're using coordinate system, we want to use the axis of the coordinate system, so we have to convert dl into dz, then we would be ready to integrate it. So I have to take this dl and convert it into dz. I can use this right angle triangle. I wasn't kidding when I told you that right angle triangles are going to be your best help whenever you do vector calculus. So I take this right angle triangle, and from this right angle triangle, it's very clear that dl or dz by dl is cos theta naught, and thus dl is dz by cos theta naught, and thus my ds element becomes r, which is a function of z, so we can substitute that function of z and theta naught multiplied by d phi. This term is nothing but r multiplied by dl, which is dz by cos theta naught. Now we are ready to integrate. This is a constant, this is a constant. We change z from origin 0 to this point, which is height h, and we change phi from 0 to 2 pi so that we make that circle. So we take this element and we are ready to integrate. Please go ahead and integrate and see whether you get the same answer you got with spherical coordinate system. So obviously using for surface element for cone, as we had in the previous video we had seen for using spherical coordinate system was much easier to use than the cylindrical coordinate system. But go ahead, practice it and see whether you get the right answer.